Okay, thanks. And I will start my my timer here. And okay, we're good to go. Yeah, so I am my name is Felipe Madsen for those who don't know me. I work for NRAO and I'm a software engineer there. I'm back for but my background is in physics and astronomy. And I'm going to tell you how we successfully made an deepest image ever of the Hubble Ultra Deep Field with an interferometer. So here's my abstract for completeness. We'll not read it now, but it's there in the talk, and the talk will be available online. So I'll start with some facts about our imaging run in December, combining resources from PATH and OSG. So it's as I said, it's the deepest radio image of the Hubble Ultra Deep Field. On the peak, we had 76 concurrent GPU jobs. So 76 GPUs were hot with our data for a while. We had a throughput of 2.7 jobs per minute, 1.5 terabytes per hour. That's the average of our fastest cycle. So this cycle will become clear later in the talk. Approximately 750 total GPU hours to make one image. And this one image is the one that's on the side here that Sanjay also showed in his talk. And he spoke about the scientific importance of this. So I will focus more on how I implemented it and what's next. On that run, we had about 1650 jobs. And that took approximately 5 days of wall clock time. We started on Monday. We had a team working on this. We had to solve a team from NRAO and from PATH, CHTC, OSG. We had a lot of people in the loop working to solve problems as they were appearing. It was amazing work. Thanks everyone. And we had 5 days wall clock time, and but the actual processing time, if you take into account all the jobs and sum everything, it was around 24 hours. But I wanted to know a little more about what was the performance of this. So I already had this this tool that I call the concurrency plot, and that I showed very briefly last year in my talk, and I want to get into more detail now. So this is a static view of this concurrency plot, and it shows transfers, it shows when the job started to run, it shows when my app started to run, it shows a critical part of my app running. It's a timeline on the x-axis, so this is this looks like very much like a Gantt plot. It is, in fact, but it shows me details of my jobs. Well, the static view is fine. It's already telling me, jobs that transfer data really quickly, jobs that transfer very slowly. But we can get into more detail with this. So I will show the actual concurrency plot. And right now you don't see anything because this is over 1,600 jobs spread over 5 days, and this is showing everything. This is trying to show everything. So there's almost nothing in the screen, but I can zoom in to particular cycles here. And so there you go. Now you see one particular batch of GPU jobs, and I will show only that. This is the one I was saying was the best cycle that had the best throughput. And see lots of jobs here. I hover the mouse over them and I can see details of that particular bar. And this is a very useful tool in identifying things that are running well and things that are not. I can zoom in even further to this part, for example, and I can see when the jobs are starting, you know, some transfers really fast. The cache is, you know, doing its job here, and there's only two minutes to transfer a reasonable something like 10 gigabytes of input data plus other, so probably something between 10 and 25 gigabytes of input data. But then there are jobs where, you know, not so good. The transfers are taking longer. And there's also, if I, you know, there's also this way longer bars. So maybe the data was not available in the cache at that time, or maybe there was something else. And so this is, I like this, but this is a way I developed to see, to identify, to quickly identify problems, and what I can act upon. And but this also will help me tell, you know, look at the complete picture of a job, and I can say, well, I can improve this or that specific characteristic of my workflow. For example, there is idle time here. And why is that there? Why is there idle time there? So the one thing that we identified from this, I think the main thing, of course, there is, you know, a lot of transfer time, and this is a serial barrier that we identified thanks to this, and also, of course, looking at, you know, just watching our jobs, we already knew that. And the serial jobs are part of the workflow. I'll get into details of that later. And this is something that we from the beginning, we said, okay, we have to improve this. But there's also this. All this is idle time, and it's like 3 hours. And that's because between one cycle and the other, we needed human intervention because some job was put on hold, some input was missing, or there was a failure in some transfer. And all this we were able to identify and correct during this run. But of course, for a production run, we need this automated. And so we've been, me and the team have been talking a lot with um, the CHTC, OSG folks in terms of how can we better automate this, because that's key to getting even better throughput. And so we'll go to the next slide here, and that analysis that I quickly showed this, let's say a demo or a quick analysis, and this, as I said, helps identify and prioritize improvement opportunities. And that's what we did. What this is, I took the future work challenges from my talk last year, and what I had in my slide, exactly the same bullets, but then the tasks that were prioritized and completer or ongoing are marked red here. And so we are working, that's one of our priorities, improve IO efficiency of grading jobs. I have a colleague that's working almost full time on this. And then integrate test new model cycle software module. That's something that I did for our new implementation, for a current implementation. I've been running tests with it. Actually, we have deployed all jobs have new software running new software, and I'll get to this quickly later. But also there is a gather barrier, as I said, and we're optimizing the DAG design to minimize that. That's already in my current implementation. And we're also investigating scalable design solutions. So these were identified by, you know, this tool helped a lot in identifying this. And so and also from an infrastructure's perspective, you could in principle use this tool, the concurrency plot, to help identifying sites or EPs with longer transfer times. Maybe the cache is not properly, maybe there is some mistake that is some misconfiguration that's leading to a lot of misses. If you combine that with unit tests designed to monitor system performance, you can probably get a lot out of that. And I've been talking with Greg Thane about that quite a lot. And well, this is a quick, I will pass now to details of the implementation, and I will spend the rest of my next 3-4 minutes in that. So this is a quick recap of Sanjay's talk, how we make images with interferometers. And that's just a reminder that we have sparse data, how a process look like, what we get once we grid an FFT and do the FFT of our data. We get an image that still has a lot of artifacts, and we do a lot of post-processing to get to the final image. Okay, so the workflow of interferometric imaging is pretty much this. If you're applying the clean method, you have an initial cycle where compute weights and a sampling function, PSF, and then you produce a dirty image. That's the one, the one that with all the artifacts. And then there is what I call imaging cycle, where you update the model and then you update a residual image by basically subtracting the contribution from the model components. And you iterate on that, typically 10 iterations, until you get to a final image. And once you're satisfied with that image, once you cannot identify anymore anything else in the residual, you call it done and restore. So quickly, the grading can be highly parallelizable. So that's what I did for the implementation, multiple graders. The development of this started with multiple CPU graders back in 2020, and there's a little bit of a timeline there. First GPU job in 2021, multiple GPUs in 22, and then we started deploying on path on 22, and then we had the science run about a year later. We have nested dogs, of course, for controlling the iterations. So this is my and now I get into the details of DAGs. And so, this is what my outer DAG looks like, just defining the jobs. So there's a partition job that it's not fully functional now, but then there's what I call initial cycle, where I compute PSF, dirty image, and all. Then there is the iteration, and the retry here is controlling that. So this is basically implementing what you see down here. Going a step further or a step down, the initial cycle has its own tag and with a prescript that will write grading tags dynamically, and then there's lots of all kinds of scripts that have to run to deal with the large number of files that are generated and all that. And then the imaging cycle is a very simple tag that's just calling one job and one sub tag that was written dynamically, and then prescript. Okay, and then the inner DAGs, they are all written dynamically, and I think that I wanted to highlight also wanted to highlight here is that there is I'm also dynamically determining how much disk space I need, and because my data partition sizes can vary, and so I came with the simple awk script to determine how much disk space each job will be requesting. Right now, my current workflows are running with 150 jobs in each of these cycles. So, and I didn't want to have one big request for everything, because I could also optimize on disk space. And there are some other highlights of the current implementation that I wanted to show here. So, for example, something that helped, and we identified from the early days of my concurrency plots that we needed, my jobs were spending some time on expanding tarbulks. And so we use the auto expand syntax from the transfer plugin, and that's this little thing in the end here. And then job configuration, we have detailed GPU requirements, so that that can be easily parsable, easily dynamically queried by HTCondor components, and assign the right resources to my GPU to my jobs. All jobs are now requesting a singularity image, and that helps a lot with avoiding errors and everything. I now, in my current implementation, I have a unified parameter file so that I don't have to deal with many different parameter files, and so also helps avoiding human errors, and they're sure to happen, and I have to, they happen more frequently back then when I had two files, for example, two parameter files. All jobs are using lightweight and specialized Libra applications. Sanjay spoke about it. It's our group's project for libraries for radio astronomy, data processing, and I am monitoring GPU utilization with NVIDIA SMI with this command. One thing that I still have to do in all my jobs is to copy the system's libcode SO1 into the application bundle. So this is an Exodus bundle, much like a container that runs my jobs and that packs all the libraries and things. And I have to copy the libcode SO1 into that. Otherwise, I get weird version mismatch errors. And what do we have for the future? We still have to improve automation. And this week I've been running pretty much the same job, but with different with my new implementation. And I got a lot of this error. Job credentials are not available. But now the fix was deployed yesterday. And between yesterday and today, thanks to the team that deployed this fix quickly, I was having lots and lots of this error. Between yesterday and today, there was none. The fix was deployed and 5 imaging cycles ran. So about 750 jobs without any innovation. Didn't have to release any jobs. There was no jobs on hold, nothing. So that was great. Applications. So one thing that we can automate still is, we have applications and convolution functions currently pre-staged manually. It may be a good case for use case for Pelican Origin. We'll discuss that. They already pull from on Origin when the jobs are running, but we could think about having some kind of automation there. I have to improve flexibility and scalability of data partition jobs. Right now, I'm not touching them. That's my next step. And also, we could be a little more efficient if we were deploying, integrating Libra containers, so that instead of using the general container image, I could use my own image with my software pre-installed. That's something we're probably going to look at in the near future. And sorry, I rushed through details of implementation, but this was my last. This is what I had to talk for you today. Thanks.